Hello. In the previous video, we found the partial fractions by, if you want, working backwards. We have our original expression as 2 over s plus 2s plus 1, and then our partial fraction as k1 over s plus 2, k2 over s plus 1. We put this together, we have k1 into all this long expression, and then we equated this, and we now equated the numerators to solve it. Now, that's one way to go. But there is a way that is actually a little easier and the method that is used a little more. So our original expression is 2 over s plus 2 into s plus 1. And we are assuming that this is, or we are trying to expand that into k1 over s plus 2 plus k2 over s plus 1. Okay, so we're trying to expand it into this. Now, to go ahead and do this, the first thing we're going to do is we'll do this one by one, and this kind of makes our life a little easier. First of all, we make our we first multiply through by one of these terms in the denominator. So for example, let's multiply everything through by s plus 2, since s plus 2 is written first. Let's multiply both sides by s plus 2. If we multiply both sides by s plus 2, we're left with 2 over s plus 1 being equal to k1 plus k2 into s plus 2 over s plus 1. Now, by doing this, we have a term here, k1. And if we wanted to find our k1, all we need to do right now is to be a little, okay, sorry, let's just rewrite this plus very well. Okay, all we need to do is just eliminate the second term. If we can eliminate the second term, we have a solution for k1. How can we eliminate this second term? We can say let our s be equal to minus 2. In other words, one of the roots. Remember, there are two roots, minus 2 and minus 1. So let s be equal to minus 2. If s is equal to minus 2, then this will this whole term here will go to 0, and we're left with our k1. So if s is equal to minus 2, we're left with k1 simply being equal to 2 over minus 2 plus 1, okay, which comes out to being minus 2. Let's do, so that's to find our k1. If we wanted to find our k2, first thing we'll do is multiply everything through by s plus 1. Multiply everything through by s plus 1, you're left with 2 over s plus 2 being equal to k1 into s plus 1 over s plus 2 plus k2. Again, we want to eliminate this first term. To eliminate the first term, we let s be equal to minus 1, which is the second root that we have. Once we set that, that gives us our k2 as being equal to 2 over minus 1 plus 2, which gives us our k2 being equal to 2. Now let's just scroll up and see. We're having k1 as minus 2, k2 as 2. Is that what we had earlier on? That's exactly what we had earlier on. Now this method tends to be a lot faster because if you had, for instance, 10 roots, if we had 10 different terms here, it's a whole lot easier to just simply be slotting in the roots one at a time. Okay, slotting the roots one at a time, it's a lot easier than having to run through this entire expansion and now equate the numerators. It's not very easy to come up with that. It's not very easy to expand out. If you had 5 terms, if you had 10 terms, it's not very easy to expand out. However, it will be a whole lot easier to use this method. Okay, so this is the better method for computing the, or for finding your k1 and your k2 terms. Okay, so that's what you have. This is our case 1. Remember that what we were dealing with were real and distinct roots. When you have real and distinct roots, you simply decompose them into parts. Now, one thing I want to mention, in my previous video, we had this expression over here, and we said that this expression is our y of s can be expanded into this expression. Now, this expression is actually rather incomplete, okay? It's rather incomplete, and let me just make a claim that we're supposed to have this as, now, not 3. So let me erase this parameter, this 3 over here, that we shouldn't talk about having a 3 over there because we are not sure what will be in the numerator there. Rather, let's have a k3s plus k4 in our numerator. In other words, something that has a first order expression in the numerator, so that now this is generalized. Okay, this is generalized in nature, and this can literally be so this expression is better expanded as this. So I wanted to correct that in this video. Okay, so I'll stop this video at this point, and then in the next video we'll now deal with real repeated roots. That's the second case.